can start thinking of calculus as the part of mathematics that wants to understand the change between quantities. You can picture a mathematician asking, how does A change with respect to B? And maybe the mathematician is actually talking about a kid running in the courtyard outside his office, and what he really means by A is the kid, and what he really means by B is a tree in the courtyard. If you look at it that way, he's really asking, how does the position of the kid change with respect to the position of the tree? Of course, being a mathematician, he has to use complicated language, but lucky for us, we can translate it for him. That question of relative movement is the foundation of calculus. It makes sense that it should be, right? Who invented calculus? Isaac Newton. Why? Because he was mad at how fast an apple's position was changing when it hit his head. Come on, you know the story. Although for historical accuracy, I should mention Leibniz is Newton's co-inventor, but the anger that led him to calculus is not as well known. Now we know that math is like music in that it has its own notation, its own way of writing. It's basically its own language like English or Spanish. So with that in mind, let's say we want to figure out how steep a mountain is. Let's say we're going for a hike and we want to invite a friend. We know that friend will whine if the slope is too steep, say if it has a slope of 2 or greater. So we want to figure out the hike's slope. We can take a picture of the hike from the side, put it into an XY plane, and trace its contour to create a line. This happens to be a straight hike. We can see that this is a line. As such, we can actually generate an equation to represent this line in algebraic terms. We know from algebra that the formula y equals mx plus b, where m is the slope of the line and b is the y-intercept, can give us our line's equation. We can find the slope by using the rise over run method. In this case, for every unit we move in the x direction, our line goes up by 1. So we rise 1 for every run of 1. And as a result, our slope is 1 over 1, or just 1. We can also see that our line intercepts the y-axis at 0, so b equals 0. If we put it all together, we have our hike's equation. Y equals 1 times x plus 0, or just y equals x. Now remember, we said the slope of our line represents how steep the line is. Well, this hike has a steepness of 1. So we can say with confidence that our friend can tag along and we can expect no whining. Now I know that you're thinking, how does this relate to calculus? Well, remember, we said that we were going to look at things changing relative to other things. Rates of change for short. Well, if you think about it, that's what the slope is telling you, right? It's saying, hey guy, if we change the x over here by 1 unit, guess what? The y changes by 1 unit too. Which tells us that the word slope is actually describing the concept of a rate of change. And as a result, is directly related to calculus, the study of patterns of change. That brings us to one of the most powerful tools in the world, used in all kinds of disciplines from the design of cars in engineering to the study of population growth in the social sciences. That tool is a derivative. Before we get into the mathematical explanation of how the derivative works, or even why it works, let's first destroy any belief that derivatives are too complex to understand. We're going to give it a test drive using our hike example so we can see that, like the word slope, the word derivative is just another way of saying rate of change. And in fact, a derivative is nothing more than a slope. The quick formula to take derivatives goes like this. If we have a function, f of x, which equals some constant c multiplied by the variable x, which itself is raised to a power n, we can take the derivative of f of x, denoted by f prime of x, by multiplying the original constant c times the original power of x, n, and using that as our new constant. Then we subtract 1 from the original power of x and use that as our new power. That's it. If you have more than one term, you do that same procedure to each individual term, making sure to keep track of your term's signs, if you are subtracting or adding that term. Applying that procedure to our hike, we start by writing y prime, so we know this is the derivative of y. Then we multiply our constant by the power of x. In this case, our constant was an implied 1, and the power of x is also an implied 1. That gives us a new constant of 1. Then we subtract 1 from the original power of x to get 0. As we know, anything raised to the 0th power equals 1, so our variable x becomes a 1. Putting it all together, we have 1 times 1, which equals 1. This tells us that the derivative of y equals 1. It's no coincidence that the slope of y also happens to be 1. A derivative calculates the slope of a line. To prove it to you, let's pretend our hike is a little bit steeper. Let's pretend that for every unit you walk to the right, you go up 2 units. We would then have a slope of 2, and since our line is still intercepting the y-axis at 0, the new equation would be y equals 2 times x. If we take the derivative, we have y prime equals 2 times the power of x, 1, which gives us 2. And for the new power of x, we have the same thing. 1 minus 1 is 0, which results in our variable x becoming just 1. So in this case, the derivative is 2, which again matches the slope of our line. By the way, if this is the hike you actually choose, remember that if you invite your friend along, you can expect some whining. What's really cool about derivatives, though, is that you can find the slope of curves. Think about it. If you want the slope of a straight line, you just look at its equation, y equals mx plus b. But what if you have a curve like y equals x squared? The slope is not obvious from the algebraic notation. In this case, you take the derivative, which gives you a generic formula for finding the slope of different points. Since the slope of a curve changes with x, by using the derivative, you can find the slope of any curve at specific points. That's the real power of derivatives, determining the slope of curved surfaces.